In this lecture, I'll show you why linear algebra is such an important part of multivariable calculus, which is sometimes called vector calculus. I'm going to assume that you've done single variable calculus and are familiar with those ideas, but I won't assume that you've had any multivariable calculus. But if you've had multivariable calculus already, then you probably had a version that avoided discussing linear algebra by disguising it in some way, since you didn't have that language yet. So this lecture will probably open your eyes to what you were really doing in that class. And if you're taking multivariable calculus after linear algebra, then this lecture will give you a preview of how the ideas you've learned here will be used in a very natural way in that subject. Let's review some ideas from single variable calculus that we may want to generalize. In single variable calculus, we study functions of one variable. There's one input and one output. The first big idea of calculus is the idea of an instantaneous rate of change. Usually we speak about instantaneous rates of change of a function f near a point A. We often think of the derivative as a slope of a graph near a point A. It may or may not exist, but if it does, we call it the derivative of f at A, and we write df over dx. Recall that the derivative df dx exists at A if the graph is locally linear, meaning if you blow up that region of the graph more and more, it looks more and more like a straight line. That should make sense to us intuitively because then you have a well-defined notion of the slope of a graph near that point. I won't remind you of the definition of the derivative, but it's a limit that basically expresses this idea. So, a function is differentiable, meaning it has a derivative, if the graph near the point can be approximated by a tangent line. Another way to think of a derivative is that it's a scaling factor that results from a small change in x producing some change in f. This change in f, which we write delta f, is approximately the derivative times the change in x, which we write delta x. This idea actually supplies us with a way to approximate a function f near a point A. Namely, if x is a point I want information about, I can replace delta x by x minus a, and delta f by f of x minus f of a, and then we will get this. From this, we see that f of x is approximately f of a plus df dx times x minus a. And that expression shows me how to approximate the value of f of x, knowing the value of f of a, and the derivative df dx evaluated at a. The right-hand side here is the equation of the tangent line to f at the point A. We've just approximated a function by something nice and easy to understand, a line. And that's one big moral of calculus, to approximate something crazy by something simpler. And this moral appears in multivariable calculus too. You just have to decide what you mean by a nice function. In multivariable calculus, the functions you work with can have more than one input variable and more than one output variable. There could even be different numbers of input and output variables. We might express such a function as a function f from Rn to Rm that takes n input variables, x1 through xn, to m output variables, g1 through gm. Each of these gi's are called component functions. And notice that the component functions are really functions of the input variables, but to save space, we usually omit writing them. Here's an example of a multivariable function. Suppose you had, for each position, xy, on a sheet of paper, 3 quantities of interest. That could be a function like f of xy equals the vector x squared times the square root of y, comma, sine of x, comma, 1. This function takes a two-dimensional vector to a three-dimensional vector. So f is a function from R2 to R3. And you see that each component may depend on some or none of the input variables. Another example of a multivariable function is one you've seen and studied in detail in this class, and that is a function that multiplies a vector by a matrix A. Here the function f of x is a times x, where x is in Rn, A is an m by n matrix, and thus ax is a vector in Rm. This function is a linear transformation from Rn to Rm. And as we've seen throughout this course, all linear transformations can be expressed as matrix multiplication. And we can think of linear transformations as the nicest examples of multivariable functions. We now understand them quite well. That's the whole subject of linear algebra. So just like in calculus, when we try to approximate functions near a point by assuming they behave like lines, in multivariable calculus, we will assume that a function near a point behaves like, you guessed it, a linear transformation, because linear transformations are nice. Just like in single variable calculus, where a function is differentiable, meaning a derivative exists, that's where there's a good line that approximates it. And for multivariable functions, a function will be differentiable when it has a good linear approximation. We won't be precise here about what we mean by good, but we can give you a picture. For instance, if you're looking at a function f from R2 to R, then it takes in two real numbers like x and y and spits out a single number like f of xy. This means the graph of this function can be represented by a surface over the xy plane. To say the function is differentiable at a point means that if you blow up the view of the graph near that point, it looks more and more like a plane. In other words, it's locally planar. For functions from Rn to Rm, differentiability means the function is locally linear. Something like this picture. Notice the function is not linear because it warps the face in a crazy fashion, but it would be locally linear if on a small scale it takes little parallelograms to little parallelograms. The square nose in this face seems to be doing this. It gets sent to a parallelogram. We can make these notions precise in a multivariable calculus class, but right now I'm just trying to build your intuition. So now how should we define the derivative of a multivariable function from Rn to Rm? What kind of object should it be? We'll take a cue from single variable calculus where a little change in f is approximately the derivative df dx times a little change in x. With multivariable functions, we'll use a similar expression, except delta f is going to be a change in the output. So it's a vector in Rm, and delta x will be a small change in the input. So it'll be a vector in Rn. So we need the derivative, whatever it is, to turn the vector delta x into the vector delta f. What's the only thing you know that will take a vector in Rn to a vector in Rm in a linear way? That's right, a linear transformation. And it's represented by a matrix, in this case, an m by n matrix, so that it acts on an n-dimensional vector and produces an m-dimensional vector. This matrix is playing the role the derivative did in single variable calculus. So the derivative is a matrix. And not surprisingly, we call this matrix the derivative matrix of f, and we notate it by writing capital df. So if f goes from Rn to Rm, can you see what dimensions this derivative matrix must have? Yes, that's right. It must be m by n because the act of multiplying by df needs to send a vector in Rn to a vector in Rm. So both the original function and its derivative take Rn to Rm. And if we replace delta f by f of x minus f of a and delta x by x minus a, then we can approximate f of x knowing f of a and the derivative matrix at a. Rewriting, we'll get this. So you see in this formula how a small change in moving from the point A to the point x produces a linear adjustment to the value of f of a, just like in single variable calculus. One question you might wonder is, what are the entries of this derivative matrix? And that turns out to be very simple. The entry in the ith row and jth column is just the partial derivative of f sub I with respect to x sub j. So we know what the matrix is. If you don't know what a partial derivative is, it's just the usual derivative if you pretend all the other input variables are constant. Let's do an example. Suppose f of x, y, z is the vector x squared plus y squared and 2xz plus xy. What is the derivative matrix df? Well, the first thing to ask is, what are the dimensions of df? I'll give you a moment to think about that. Well, since f goes from R3 to R2, the matrix df must be 2 by 3 in order for it to behave right. Then we can compute the partial derivatives. Notice that all along the first row of df, we are taking the derivative of x squared plus y squared with respect to x first. Then we do it again with respect to y, and then again with respect to z. So that's 2x, 2y, and 0 in the first row of df. Similarly, the derivative of the second function, 2xz plus xy with respect to x, y, and z, gives a second row of df as 2z plus y, x, and 2x. So df is this 2 by 3 matrix. And if you ask me to evaluate df at specific points, like 1, 2, 3, I can plug those in and I get the matrix 2, 4, 0 and 8, 1, 2 in the rows. This matrix will give a good idea of how f of xy behaves near the point 1, 2, 3. Now you can check 1, 2, 3 goes to the point f of 1, 2, 3, which is 5 and 8. And any vectors based at the point 1, 2, 3 get mapped to vectors based at 5, 8 using the matrix df. So if I want to estimate the function value of f at a nearby point, let's say x is the vector 1.1, 2, and 2.8, and I know f at the nearby point, a equals 1, 2, 3, then I can use this approximation, which says f of x is approximately f of a plus an adjustment that is the matrix df at a times the change in input, which is x minus a. So then f at 1.1, 2, 2.8 can be approximated by f at 1, 2, 3, which is 5, 8, plus the 2 by 3 matrix derivative evaluated at 1, 2, 3, times the vector displacement, which is 0.1, 0, and minus 0.2. If you add that up, you'll get the vector 5.2, 8.4. And you can compare the actual value of f at the point 1.1, 2, and 2.8, and you'll find that it is 5.21, 8.36. So our estimate was actually pretty good. Now once you've realized that the derivative of a multivariable function is a matrix, then a lot of other things begin to fall into place as analogies of the single variable case. For instance, remember the chain rule from calculus? It answers this question. If f is a function of some variable x and x is a function of some variable t, then how does f change if you change t? This is the rate of change of a composition of functions f of x of t. Well, it turns out you just multiply the derivative so that df dt is df dx times dx dt. And sometimes people wonder why the chain rule involves a product. Actually, it makes sense that it's a product because one way to interpret this chain rule is if you knew that Xavier runs twice as fast as Tom and Frank runs 3 times as fast as Xavier, then Frank must be running 6 times as fast as Tom. The factor 6 came from multiplying the factors 2 and 3. We've used the idea here that the derivative is a scaling factor, so compositions should multiply them. Well, for multivariable functions, something similar happens. Suppose you have a function f going from Rn to Rm, and another function g going from Rm to Rk. Then, if x is a point in Rn, how does g of f of x depend on x? The function g of f of x is the composition of g and f, and it's notated g circle f. Well, just like in the single variable case, you multiply the derivatives of g and f, which in this case are matrices. It should be plausible that you do this because the determinants of these matrices describe the approximate scaling factor of these transformations. Then the scaling factors should multiply if you do f first, then g. The dimensions of the multiplication make sense here too, because a product of a k by m matrix and an m by n matrix is a k by n matrix. If you've learned the chain rule without knowing matrix multiplication, then you probably learned a complicated formula for the chain rule, sometimes called a tree diagram. Notice here how the language of matrices makes it very easy to describe the chain rule. And conceptually, we have a much clearer picture about what's going on, too. Here's another nice generalization of calculus ideas to multivariable calculus, where linear algebra gives us some insight. Do you remember Taylor polynomials? They're those polynomials that are used to approximate a function f near a point A when you know the value of the function and some of its derivatives, but you want to approximate the function at a nearby point. In calculus class, you learned a formula for finding these polynomials by taking successive terms of the Taylor series. The first few terms look like this. We won't discuss how we derive these terms here since you can learn about them in calculus, but we make some observations. Notice the only variable in this expression is the x because the point A is given. Each successive term involves one more derivative of f than the prior term. The Taylor polynomials are what you get when you truncate this series after a certain number of terms. So for instance, if you just take the first term, you get a constant function, often called p0. It shares the same value as f does at the point A, and then adopts that value as a constant value everywhere. If you take 2 terms, you get p1, which is the tangent line function that shares the same value and slope at A. And if you take 3 terms, you get p2, which is the best fitting quadratic that shares the same value, first and second derivatives, with the function f at A. Similarly, taking the first 4 terms gives you p3, a cubic polynomial that shares up through the third derivatives with the function f at the point A. And if you look at the picture, you get a sense of how these polynomials attempt to approximate the function f. Near A, they get better and better as you increase the degree of the polynomial. Taylor polynomials are pretty awesome. Engineers and physicists and economists and other scientists use Taylor polynomials to help understand what some crazy function is doing, since polynomials are easier to understand. And they're used to estimate functions when we know some derivatives at a point and you want to know the value of the point nearby. Have you ever wondered how a calculator remembers all the values of sine or cosine? Well, it doesn't. Often algorithms for calculating special functions like these rely on special series like the Taylor series. Now, you may wonder how this might generalize when you're dealing with a multivariable function. Let's say you have a function f going from R2 to R, so it has only one output value. We'll assume f has continuous second partial derivatives. Suppose you want to approximate f near the point A with vector coordinates a1, a2. Here's the formula for the Taylor polynomial of degree 2 that you often learn in a multivariable calculus class if you haven't learned linear algebra yet. The notation f sub x at a stands for the partial derivative of f with respect to x evaluated at a. Similarly, f sub xy at a is a second partial derivative, which you get by taking the derivative of f with respect to x and then again with respect to y. What you'll notice about this formula is that it looks similar to the situation for single variable calculus, but it's way more complicated. Also notice this would be an even more complicated expression if you had a function of more than two variables. But this can be written much more neatly if you know some linear algebra. For then we can just write this as three terms like this. Here the vector A is the point you want to expand near, the vector x is another point, and delta x is a displacement vector, the difference between the vector x and the vector A. The initial term is the constant term f of a, the value of f at the point we care about. The next term is the derivative matrix times the displacement vector delta x. This is the linear term. Notice for a function from Rn to R, the derivative matrix is a vector of partial derivatives. The last term is 1 over 2 factorial times delta x transpose times the matrix HF times delta x. This is the quadratic term. The matrix HF is called the Hessian, and it's a square matrix whose entries are all the second partial derivatives. So for functions depending on two variables x and y, the Hessian would look like this. Notice that f sub xy will equal f sub yx if under mild conditions, which means the Hessian matrix is real and symmetric. So our Taylor polynomial is very succinct, and it holds for any number of input variables and one output variable. We can learn a lot from looking at the Taylor polynomial. In particular, we can see how to find maxima and minima. In fact, let's derive the first and second derivative tests for multivariable functions. Glancing at our Taylor polynomial, we know maxima and minima cannot occur if df is not the zero vector. That's because depending on how you choose delta x, the linear term could either be positive or negative. So f of x will be both above f at a and below f at a at various places. So f of a cannot be a local maximum or minimum. So the only places where maxima and minima can occur is where df is identically the vector 0. We call these the critical points, where df equals 0. You can see this is the same as setting the partial derivatives equal to 0. In other words, the graph of the function is horizontally flat near a critical point. This is just like what happens in single variable calculus, where you set the derivative to 0 to find critical points. Only now we're setting df equal to 0, which means all the partial derivatives equal to 0 as well. Now that we have critical points, how do we tell if the function is a maximum or a minimum or neither? Well, we look to the quadratic term just like in single variable calculus. Remember that the linear term is now 0, so only the quadratic term will tell us if f of a is a local maximum or a local minimum. So we inspect the Hessian for clues. We want to know if the quadratic term is always positive, for then f of a will be a local minimum, as f of x is going to be bigger than f of a. Or, if the quadratic term is always negative, then f of a will be a local maximum. But if the quadratic term is sometimes positive and sometimes negative, we'll have something else entirely, and that's what's called a saddle point. Note that if the Hessian HF were the identity matrix, then delta x transpose times delta x is going to be positive no matter what x is, since that's just the dot product of a vector with itself, which you may recall is the length of a vector squared. So in that case, a quadratic term is always positive, so you'd have a local minimum. Now, if HF is not the identity, we can still see what's going on because we might be able to find special directions V in which HF times V is just a multiple of V. Do you remember what that's called? Yes, it's an eigenvector. And since the Hessian is real and symmetric, it's orthogonally diagonalizable with all real eigenvalues. So if delta x is a eigenvector V with positive eigenvalue lambda, then the action of HF acts on it like scalar multiplication by lambda. So we just get the dot product of the eigenvector V with itself times lambda and a half. So the quadratic term will be positive for any vector in lambda's eigenspace if lambda is positive, including if we negate the eigenvector. So along the eigenspace, you can roll forwards or backwards from the point A, and you'd still be increasing the value of f. It's concave up along that eigenspace. And if the eigenvalue lambda were negative, then rolling back and forth along the eigenspace will move the function value lower. So it's concave down along that eigenspace. So the signs of the eigenvalues of the Hessian tell you something about the directions in which the function is concave up or concave down. Turns out, though we won't show it here, that if all the eigenvalues of HF are positive, the critical point is a local minimum. And if all the eigenvalues are negative, then you're at a local maximum. And if you have some negative and some positive eigenvalues, then you have what's called a saddle point with some up and some down directions. For a two-variable function, the Hessian is 2 by 2, and an easy way to check the eigenvalue signs is to, guess what, take the determinant, which is the product of the two eigenvalues. And so if both eigenvalues are the same sign as they are for a maximum or minimum, the determinant will be positive. Also, if the eigenvalues are different signs as they are for a saddle point, the determinant will be negative. And so what is the determinant of the 2 by 2 Hessian? Well, if you think about it, it's just f sub xx times f sub yy minus f sub xy squared. You may recognize this quantity if you've learned about the second derivative test for multivariable functions. It's called the discriminant, and it's the usual quantity to check. But most people don't tell you it's just a determinant of a 2 by 2 Hessian. Let's finish with an example. Suppose I want to find a point in R3 on the plane x plus 2y plus z equals 6, closest to the origin. A solution would start by noting that I want to minimize the distance from the origin, and that is given by the distance function from 0, 0, 0, which is the square root of x squared plus y squared plus z squared by the distance formula. Now we note it's often easier and equivalent to minimize the distance squared, which is the simpler expression, x squared plus y squared plus z squared. To restrict the point xyz to the plane, we substitute z equals 6 minus x minus 2y. And then we find that the function we want to optimize is f of xy equals x squared plus y squared plus a quantity 6 minus x minus 2y squared. That's a two-variable function. So to find its critical points, I'll set df equal to 0, which means setting the partials f sub x and f sub y equal to 0. Take a look at these calculations for f sub x and f sub y and see if you agree. When you solve these equations for x and y, you will get x equals 1 and y equals 2, and that will imply z equals 1 if you use the equation of the plane. You might pause here and try this. Now, we found exactly one critical point, 1, 2. Is it a minimum for f? Let's check the determinant of the Hessian, which is f sub xx, f sub yy, minus f sub xy squared. If you calculate f sub xx, you'll get 4. For f sub yy, you get 10, and for f sub xy, you get 4. So 4 times 10 minus 4 squared is greater than 0. So 1, 2 was a local minimum as desired. If you think about how a point and a plane sit, you'll realize if you find a local minimum, it must be a global minimum as well. So 1, 2, 1 is the point on the plane closest to 0. Multivariable functions highlight a big theme of linear algebra, that we like approximating nonlinear things by linear things. That idea is the foundational idea behind all applications of the derivative matrix.